And now we come to a talk which tells us what the Bela instrument on Bepicolombo can contribute towards a better determination of Mercury geophysical parameters. And sorry, but your name is very hard to say.
Yes. So good afternoon. I'd like to talk about the impact of Bepicolombo Laser Altimeter on orbit determination of MPO and also on Mercury geophysical parameters. This work has been done at the University of Bern. So this is the table of content. I would talk about objectives, MPO orbit modeling, Doppler observation, laser altimeter simulation, and conclusion at the end. So as you well know, Bepicolombo is the first European mission to Mercury, and Bela is Bepicolombo Laser Altimeter. It sends a pulse to the ground, and from the return pulse, it calculates the time of flight and also the pulse energy and the pulse width. The goal of our work is, first of all, the estimation of performance of the instrument in flight. So by performance, I mean creating a digital terrain model, the surface roughness, local slopes, and albedo variations. And also, we want to contribute to orbit determination and Mercury geophysical parameters. The tool that we use in this process is Bernese software, which is developed at the University of Bern, Astronomical Institute of the University of Bern. We use a closed-loop simulation based on previous studies by Marabocci and Cicalo, and we are using a similar condition, but we are trying to do some improvements, like we are using an improved instrument model. We are using an improved planet shape model containing the local slopes and albedo, and we are using the laser altimetry both on the crossover points and directly. So we also want to contribute to Mercury geophysical parameters, which can improve the orbit in an indirect way. This is the approach. First of all is the blue part. We start from the modeling the orbit of MPO. We model are the gravitational and non-gravitational forces that act on the orbit, and create a more model of the orbit. I will talk about the rest later. So here you can see the amplitude of the acceleration that of the forces that acts on the MPO, and you can see the biggest one is Keplerian forces, and the rest are the effects of the solar radiation pressure, planetary and radiation, and other forces. And for the solar radiation pressure and IR radiation, we use a micro model for the spacecraft, which has 33 surfaces with area and normal direction, and also with optical properties in visible and IR properties. This model is prepared by Valère. This is a comparison between our modeled orbit and ESA's orbit. So you can see that after 1 day of propagation, we have about error in the level of centimeters. After we have the orbit, the next step for us was to create an observation model, a synthetic observation model based on this orbital model. So the synthetic observation model contains Doppler observation and laser altimetry observation. And we want to use this observation model to do a precise orbit determination. So first of all, I will focus on the Doppler part, and then I will go to the laser altimetry. This is a simulation of the Doppler observation after 19 days. 90 days, and as you can see, we have some, this is a two-way Doppler data, and we have some parameters to change. We can do it in different frequency band. We can add white noises on the observation, and we can change the visibility conditions. So for example, here, you can see that when the spacecraft is behind Mercury, it's in eclipse position, you don't have the Doppler data. Using this Doppler data, we tried to reconstruct the orbit. So we did first some simple tests. The first simple test was we used a full force model with a gravitational model up to degree and order 50, solar radiation pressure, IR radiation albedo effect to produce a synthetic Doppler data. And we used the same model with the same initial condition as our priori knowledge of the orbit. So we expect, as you can see, that we directly go to the noise level. We directly go to the noise level, and so the model works fine here. And the next test that we did was we used again the same model, the same full force model for both synthetic reality and our priori knowledge, but with different initial condition. And here you can see that after some iteration, the red line is the first iteration, and you can see after some iteration, you can go to the noise level. This plot is zoomed in this part, so you can see different iterations, and this is the we are using the daily arc, so this is the first arc, and this is the second arc. This was on Doppler data, and this is on position. Then we used, again, just the Doppler observations to do a sensitivity studies, and with a reduced gravity field, with a model with no solar radiation pressure, and with a model with no planetary radiation pressure. And we did it in, we reconstruct the orbit using this situation, and as this is the Doppler residuals between that comes from the reality, the synthetic reality, and the model, the orbit after reconstruction. So this is the RMS of the orbit. What happened? This is the RMS, and in the last test we used no solar radiation pressure and no planetary radiation pressure, but we introduced some empirical acceleration, and as you can see that this empirical acceleration can observe the effect of mismodeling that comes from no solar radiation pressure and no radiation pressure, and the RMS will go to a very low level. After the orbit modeling, the main part is the model of the observation. The model of the laser altimetry observation. So we use the orbital model. We use an instrument, a model for the instrument, and a planet shape model, digital train model, to produce this laser altimetry data, synthetic laser altimetry data, actually. So we wrote a routine in Bernese software to calculate the range with respect to time, taking into account that the position of a spacecraft will change with respect to time, taking into account that the shape model is different in different positions. We have different radius in different positions, and take into account the attitude information and also the position of instrument with respect to center of mass of the spacecraft. So taking into account all this condition, our model calculates the two-way range. And also in our model, we include the instrument model, which contains range model and the effect of probability of false detection. Here is the latest probability of false detection, simulated probability of false detection based on our laboratory test data. So in this column, you can see the distance to Mercury in kilometers, and this is the pulse, the return pulse energy that the instrument receives. And here is the probability of false detection in different conditions. What do I mean by probability of false detection? Sometimes when the instrument receives a signal, the amplitude of the pulse is lower than the amplitude of the noise. So the instrument detects a wrong, a noise instead of false. So we call it a false detection. So the false detection depends on the pulse width of the return pulse. So if you have a narrow pulse or normal pulse, we can see that with our latest results, we can see some pulses up to the altitude of 1200. We used this table, the latest probability of false detection data, to use the instrument to make the instrument model, and here is the simulated range. You can see the green line is our model is the result without using the instrument model, and if we use the instrument model, you can see some red points here, and which show you the effect of probability of false detection on the result. So you can see in higher altitude, we will have a lot of false detection. So, but in lower altitude, somewhere like this, you can see that the red points are exactly on the main green lines. So we don't have any false detection here. For using laser altimetry for orbit improvement, one usually use crossover points. So crossover points are locations where two space-ground track intersect, and they are advantageous because two measurements should yield the same planetary radius. So we can just remove the effect of planetary radius at these special points. So we have to write, we wrote a code to calculate these positions, and it was a hard task because the code has to be fast and accurate, and because we have to run it several times during our orbit reconstruction. So I used several approaches to finalize my codes. I don't have time to explain all of it, but if I use a wrong approach, you can see that you can see a lot of wrong crossover points that detects here. And if you use a right approach, you can see that all of them will be concentrated on the pole. I will zoom in this part, and you can see that they will be something like that. These are the crossovers from 1 day of orbit simulation. So at the end, when we have our observation models containing the Doppler data and laser altimetry data, we can first do an evaluation of performance of instrument in orbit, and then we can use this to do a precise orbit determination, gravimetry, and at the same time estimate the impact on the Mercury geophysical parameters, and all these together can lead, for sure with topography, can lead to more information about planetary interior dynamics. So I conclude, we produced MPO orbit based on a full force model. We estimated Doppler data. We are able to reconstruct the orbit using Doppler data. We estimate laser altimetry based on Bella characteristic coming from laboratory test, and we can compute the crossover points based on given orbit. And the next step would be to use this altimetry model at the same time with Doppler data to do an orbit reconstruction, both using both Doppler and altimetry. And we also want to do a recovery on orbit and also on Mercury geophysical parameters. Thank you very much.